Okay, in this video, we're going to look at arrays and slices in Go. And this is one of the more, I think, challenging things for C or C++ programmers to transition to Go because what you sort of expect for the syntax to mean, it doesn't. But hopefully we'll be able to explain things clearly so you'll know really what's going on underneath the hood when you create an array or a slice in Go, and we'll be able to handle these things with ease. Right, so this program here is going to create an array of 10 integers. So you'll see we have numbers, which is an array of 10 integers. In Go, different sizes are different data types. So an array of 10 integers is different than an array of 8 integers. With an array, there's no sense of array of any size. We'll see those later with slices, but with arrays, there is a fixed size that goes with them. So we've created this array of 10 integers. We're going to have a loop to enter them. As with C and C++ and many other languages, these arrays are zero-based. So we have numbers 0 through numbers 9 are those 10, and we use the square brackets to index into the array. We're going to call this getNumber method. So this getNumber method does is it's going to print out the prompt, then it's going to read from the keyboard whatever the user types, and it's going to try to put it in an integer variable. If there's no error, it will break out of this loop and return the number. If there is an error, it'll read the rest of the line and discard it, print invalid input, and then ask again. So this will loop until you enter an integer. So if I say like run average 10, and then I try to type something that's not, it reads that A, it's like, no, you're not an integer. It trashes the rest of the line, prints the message, comes back around. So let's type some numbers here. And what you might expect is, I had this routine called sort numbers. It actually does sort this array, and yet when I go to print it out, it's not sorted. And that's sort of one of the surprising things. That's because when we call this method with an array of 10 numbers, you may recall from our function video that Go is a pass-by value language. So it actually makes a copy of the entire array, sorts the copy, and then leaves the original unchanged. So if we don't want that to happen, we need to do the pass-by value. So we'll say I want to pass an array of 10 numbers. Then down here we have to pass the array, the address of the array. So here we're saying we have a pointer to an array of 10 numbers. Here we pass the address of the array, which will match that pointer. We can then save that. We'll build the function. One, 4, 7, 12, 6, 10, 5. And so you'll see this time it does, in fact, sort the numbers. So that's one of the interesting things to know about arrays. Now, actually, most of the time, you do not want to declare an array in Go yourself. You want to instead declare a slice, which will have an array which forms the storage for the slice, but you'll want to use the slice rather than the array. In fact, one of the reasons that we have this sort numbers method here is because the sorting routine that's built into Go expects a slice rather than an array. So let's switch over here to this program. So now we're going to import the package slices. We use that same get number. Here now, in order to create the slice, we use this make. This says make 10 will be the number, and then it's a slice. So bracket, bracket, int, so it'll be a slice of integers with length and capacity 10. We then read in those 10 numbers. We can call slices.sort. You'll see it sorts it just fine. So let's talk a bit more about what this slice really means. So we talked about arrays. Arrays are these fixed capacity things. We saw that with our method. We also saw sort of, perhaps we're surprised by the fact that when we did that sort, it sorted the copy and not the original array. And so when we have an array, we have this contiguous block of memory holding the values. So basically the red in this picture is the array. And behind every slice, there is an array. But the slice gives us a view of the array. So the slice has a pointer to the storage in the array. It has a length and it has a capacity. And so that capacity might actually be smaller than the length, so we might allocate more space and not be using all of it right now. That's what these two things represent. Now to demo that a bit more, I will show you this slice visualizer. So I've created a little program here in the slice visualizer. This has an array of 5 strings. So we have these Unicode emoticons, 5 strings. Face is then a slice, and when we create a slice, we can create a starting point and an end. Interestingly, that includes the 1 but does not include the 4, so it's like a closed comma open interval. So 1 will be part of the slice, 4 will not be part of the slice. So you see that here when I call this visualize method and I give it the array with the 5 strings. Face starts, so the pointer starts at this first one, and 1 through 4 meant we really only included 1 through 3. So the length of this is 3, 1, 2, 3. The capacity, however, is still 4. So the array had 5 elements. When we sliced it, we reduced the capacity to 4. Now, when we do a slice, we can only slice forward. We can't go backwards. So starting with face, we can't ever from face get back to the original array. We could slice A again differently, but we can't from the slice face get backwards before its beginning. All right, so now what I will show is what happens when we do append. So append allows us to add something to the end of a slice. You'll note that when we append to face, it assigns that back to face because we're changing things about face. We might be changing the underlying storage. We're definitely changing the length. So we'll go ahead and uncomment this, comment this, visualize it now. So now what you'll see is that we've actually replaced this last character. The slice now has both a length and a capacity of 4. So this smiley face replaced the finger pointing to the right. And so at this point, there's no more room for when we append again. I'm going to create a second slice called plant, which will be 4 integers. And a third slice called nose. Nose will take 1 through 3 of face, and then we'll visualize that. So this is what we had now, right? We have array A, we have face, which starts pointing at the first element through the end of the array. All right, so what happens then? When we make plant, plant comes over here. It's an array of 4 integers. They're initialized to 0 automatically. They start at 0, and there's both a length and a capacity of 4. Nose, which is going to be this slice here, is face 1 and 2, right? So it's a length of 2. But face of 1 is actually A of 2. So if you look at the underlying storage, which really comes from A, face, or nose, excuse me, will actually start pointing at element 2 of A, which was element 1 of face. Then if I attempt to append to face, so face is here, you'll note face is full. So we're going to visualize this again with A, face, nose, and plant. So A stays the same. When we append to face, face was full. So face had to create a new backing array. So here, instead of having 5, it's increased its size to 8. Often it will double this. It looks like it's done slightly less than that here. And then in this new array, face now points to this new array and has this explosion character in it. So whereas before, modifying face modified A, now that we've done this append, face actually points to a different array. So anything that happens now to the slice face will not be shown in the slice nose or in the array A. So that's something to watch out for when you're dealing with these slices is things that originally were pointing to the same memory may end up not pointing to the same memory if you do this append function. All right, so that'd be something to play around with, make some slices, do some sub slices, do some append, and see what happens.